All right, we're back. So now we're going to move on to talking about simple linear regression. And we're interested in this kind of analysis when we want to fit a straight line to a cloud of points. And in this case, X and Y are continuous, so similar to correlation. We're going to fit a line so that the points above and below the line are equally spaced. And the key is that we're going to fit a line because Y is dependent on X. And we're going to create a linear function that will allow us to predict values of Y as values of X change. And so here's an example. You can see there are about 10 points and there's a line that's been fit and it's been moved around so that about as much space, there's about as much space between points in the line above and points in the line below. And what we can do then is we can calculate the equation for the line. So this should be familiar to you. Y equals mx plus b is the equation for a line. X and y, of course, are our variables, x and y. And m stands for the slope of the line, the rise over the run. And b stands for the y-intercept, where the line actually intercepts the y-axis. What's cool about linear regression is that the point x bar, y bar, so the mean value of x and the mean value of y, will always be right on the line. And simple linear regression, its whole goal is to minimize the distance between every point in your data set and the line that intersects the points. So the first thing that we're going to talk about is how much variation there is in the data set. And just like we talked about variation in a data set before, we're basically going to take each point in our data set and we're going to call it a y sub I. And we're going to take the deviation between the point and the mean y bar. Okay, so basically y bar is going to be this horizontal line that you can see here. And we're going to take each point and subtract it from the mean y bar. And we're going to sum from from I equals 1 to n of every value y sub I minus y bar squared. And that's going to give us the variance. And so here we can see every point y sub I, or the little black dots. The green line is y bar. We're going to take the distance between the points and the green line, and that's represented by the little dotted red lines on the graph. We're going to add those all up, square them and add them all up. And that's going to give us the variance, just like it did in our other data sets. But in this case, we're going to call it the total sums of squares. And again, it's a sum because of the sigma, and it's squares because the values are squared. But in this case, just think of it like the total variation in the data set. Then we're going to calculate another sums of squares. And this is the fraction of variation in the data set that can be explained by the line itself. And so we're going to look at, instead of all the points in the data set, we're going to look at all the points along the line. So at each value of x sub I, there's a value of y sub I, but there's also a predicted value of y right along the line. And we're going to call those values y hat sub I. So think about all the points along the line as predicted values of y, or y hats. And basically then we can compare all of those values along the line to the mean y bar, okay? So if we subtract y hat sub I minus y bar, then we get what's called the sums of squares for the regression. And so it's the sum from I equals 1 to n of every predicted value y hat sub I minus the mean squared. And this tells us how far off that line is from 0. Now, if the y hats were all along a flat line, right along the mean value, then we would add these all up and we'd get a very small number, or maybe we'd get 0, right? But as that line is steeper, we get more variation between the regression line and y bar. That increases the sums of squares due to the regression. Okay, so we're seeing a stronger relationship between x and y. And that could go in the positive direction or in the negative direction. And the last piece we're going to talk about is called the sums of squares error, or residual. And so in this case, we're going to look back at those points again, y sub I, okay? And we're going to look at all of the points along the line. And now we're going to add up how much variation is there between each point and the line, not the mean this time, but each point and the line. And so the difference between each point and the line would be y sub I minus y hat sub I. And that could be represented by these little red lines, right? And so we would call this the sums of squares regression. And it would be the sum from I equals 1 to n of every value y sub I in your data set minus the predicted value of y on the line for that same value of x. And then you would square all of those and add them all up. And this gives you how much error, how much noise is there around the line, right? So if all the points are lined up right along the line, you'd have a very small residual error. But if they're really scattered really widely, then you might have higher error. Okay, so it's a measure of how well the line, the points fit the line, basically. And the best fit line will minimize this residual error by kind of tweaking it back and forth, rotating it until the amount of space above the line and below the line is relatively equal. So simple linear regression, it's important to understand the null hypothesis. The null hypothesis for simple linear regression is that the slope of the line is equal to 0, that there's no relationship. As you change x, you see no change in y in the positive or the negative direction. Now, the alternative hypothesis is that the slope of the line does not equal 0. Okay, and so that's how you would line out the hypotheses for a linear regression. It's all about the slope of the line. Now, for correlation, it's a little bit different. The null hypothesis for correlation is that the two variables are the null hypothesis would be that the two variables are not correlated, and the alternative hypothesis would be that the two variables are correlated. So it's almost so silly that I meant, I didn't even make up a slide for the correlation hypotheses, but it's important to know that the null hypothesis would be no correlation, kind of just a scatter shot, and that the alternative hypothesis would be a significant correlation. So you can put all of these sums of squares together in what's called an analysis of variance table, because you're analyzing where does all this variation come from? Does it come from the regression line? Is it error around the line, or how much of it is this total variation? And so these are just the same equations that I already told you. They're just written in the table format for sums of squares for the regression, the error, and the total variation. But what I wanted to talk about is that there's a degree of freedom associated with each of these sources of variation. And regression is relatively easy to remember because the degrees of freedom for a regression is always 1. And the degrees of freedom for error or for total is always n minus 1. The degrees of freedom for error is then n minus 2. And what we can do with the sums of squares and the degrees of freedom are calculate two important values called the mean squares. The mean squares for the regression and the mean squared error. And basically, these are just the sums of squares for each thing divided by its degrees of freedom. And the reason that you need the mean squares is that once you have those, you can put the mean square for the regression on top and then in the numerator of a ratio, and the mean squared error on the bottom in the denominator. And when you divide those two numbers, you get what's called an F ratio. And the F ratio is similar to a t value. It's similar to a chi-square value. The F ratio is our statistic. That's what we're going after. And then we would compare our value, our calculated value of F, to a distribution of F values. And that's what I'll show you next. So here's the F distribution. You can see that sometimes it's this weird kind of very J-shaped curve. Sometimes it's a skewed function. And then as the degrees of freedom get larger and larger, it approaches a normal distribution. So the distribution changes quite a lot as the degrees of freedom change. Most of the time, it looks like these blue and green lines, and it's kind of down in the bottom corner and skewed to the right. So what you would do is you would take all that information from your ANOVA table, calculate your F distribution, and then you'd compare it to a table of F values. Now, F tables are a little bit harder to read because there's 2 degrees of freedom that you have to track. There's the degree of freedom in the numerator and the degree of freedom in the denominator. Now, remember, the F ratio is it's a ratio of the mean squared regression divided by the mean square error. And so it's the degrees of freedom associated with those 2 terms. The regression degrees of freedom are in the numerator, and the error or residual degrees of freedom are in the denominator. And if you look at this table, across the top it says numerator degrees of freedom, and along the side it says denominator degrees of freedom. So for example, for the most part, in the numerator, you would be looking for 1, and then in the denominator, you'd be looking for some larger value. It looks like I have grabbed an F table that doesn't go to 1, so I'll make sure that I get one that works better for you. There's tons of these F tables out there. You always have to make sure you're looking at the right one. And so you would find your degrees of freedom across the top and your degrees of freedom across the bottom, and that would tell you somewhere in this table a critical value of F when the p-value is equal to 0.05. And as long as your F value that you calculate is larger than what's in the table, you can reject the null hypothesis that the slope is in fact not 0. So that's how regression works, how correlation works, how to calculate the F ratio and how to compare it to a table of an F distribution, and how to decide whether you're going to reject or accept your null hypothesis.